Good. All right. So this is me. I went directly from graduate school to UC Davis, first as a lecturer, and eventually I learned crystallography from a professor who was there. I didn't do it as part of my PhD work. I was interested in computational chemistry as a PhD student, but I got kind of turned off by that, I think in part because the computers were so basic in those days that it was a lot of work. You know, you had to carry around big boxes of IBM cards, and it was slow. Nowadays, the work that I did in my PhD thesis I would do in a week. You know, it's just changed so much. So a lot of the developments in crystallography are equally changed over time because of computer changes. So I'll tell you some stories about the old days, like we were just discussing as we go along. So our interests do overlap quite a bit. I think in organic chemistry, I've also done a lot of porphyrin work. And when Sankar was a postdoc in our department, he was doing a lot of porphyrin structures. And we both enjoyed those a lot. And in the last, 40 years or so, I've been doing quite a bit with Fullerenes. And I'll tell you more about those also as we go along. OK, so here's Sankar. Now you see he was in Davis in 2001, 2004, right? OK, they all know you. But since you all know him, I thought you'd enjoy these pictures. So this was, while he was in Davis, we took a trip to our cabin, which is up in the mountains. And there's snow. Yes, you can see snow. And sometimes I often take students up there, and it's really wonderful to get to know everyone on a sort of personal level. Sometimes people who've never seen snow before get to see snow, or go skiing even. So you can see it doesn't look any different. It looks just the same. And this was a dinner at my house after the person who's sitting sort of on the center right, Dave Pham, passed his QE, his qualifying exam. My hair was a little redder in those days. But you recognize all those folks, I'm sure. Curiously, I think that's your beer there. Yours. Or maybe it's not yours. OK. And then in 2001, I think, you came back to Davis, wasn't it? Or 2010. Right. So there we are, downtown Davis, and on the right is Professor Alan Balch, who was actually his person who really directed his work besides me, who helped him with crystallography. OK, and then this was the lab kind of about the time you were there. The two people on the left were my students. We both did a lot of X-ray work. Christine, who's on the very left, is now a beamline scientist at one of the most fantastic synchrotrons in the US. It's at UC Berkeley. And she and I still collaborate quite a bit. I go to the synchrotron as well. Maybe towards the end of the course, I'll tell you more about synchrotrons. And now we currently have 3 single crystal diffractometers and 1 powder diffractometer in this room and in the room across the hall. They're all heavily used. We probably have 30 to 40 people at one time who are using these instruments. And they don't just get the data and then solve the structure. They actually do everything from growing the crystals to picking the crystals to collecting the data and everything. And they take away some valuable information, I think, by doing the whole experiment. So I'm very much in favor of that. Sorry, I know it isn't working out here, but it's a good model if you could do it. We do have a full-time crystallographer who supervises this and takes care of the maintenance and everything. So anyway, so what we'll focus on is what I call small molecule crystallography, but of course there are other branches. Back in the old days, 10 or 20 atoms in a structure was considered plenty, but now we can go up once in a while to as many as 400 atoms in a structure with today's computers. And another branch is, of course, macromolecular crystallography, or some people would say it's biological crystallography. And then there's powder diffraction. So if you cannot grow a good crystal, you may be able to grow microcrystals, which would then be powders, and you can get some information, but not quite as definitive the information as you get from single crystals. But we also do some of that. There is a lot of overlap, of course, between small molecule crystallography and macromolecular crystallography. Like if you end up taking a job in the drug industry, which does use crystallography, there may be a small molecule involved, but also a large molecule, which is, the, what do you call it? It'll interact with it, and then you end up doing both. So it's good to know both sometimes. But anyway, we'll focus on small molecule crystallography in this class. So then, maybe I don't have to tell you this. Why are we so excited about doing this experiment? Particularly the organic chemists like to know exactly what they made. And maybe that's where it ends. They don't really care much after that. But if you have the wrong atom, for example, usually you can identify the correct atom. You get the exact formula. Of course, you get bond distances, bond angles, dihedral angles, all of those kinds of things. Also, I think especially interesting are what we call the non-covalent interactions. So these are between molecules. Things like hydrogen bonding, pi-pi interactions, that sort of thing. I love looking at those. And if you want absolute configuration, and if the crystal is a single enantiomer, you can get that information much better than ever before. Used to be very difficult. But nowadays, you can actually do it with even all light atoms, which didn't used to be the case. And property structure relationships are another very interesting part. And sometimes you even discover new chemical bonds, like quintuple bonds and things that haven't been seen before. So those are some of the things that we like. And again, this is this program that is called Global Initiatives of Academic Network. I can never remember what it stands for. I usually just call it, GIAN. Anyway, that's what brings me here, and so I'm really happy to be here, and glad to see all these shining, interesting faces. And I'm going to switch to a different slide now, so let's change this. Okay, so don't really need to say much more about this one. This was the first time that crystallography was actually used as a word, as far as I could tell, in 1723. But it wasn't crystallography like we think of it, because really it was just noticing that there were particular shapes to crystals and identifying minerals that way and that sort of thing. Sometimes they're cubes, sometimes they're tetrahedra, hexagons, and so on. Actually, prior to that, some people thought that crystals were little animals, that they grew like little animals, but they were so small that we couldn't see that they were animals, but they would grow. And they also thought that diamond was actually just another kind of ice, until they realized that you didn't actually melt diamonds, and then they decided it wasn't the same thing, but they kind of looked like ice. So it really was quite a while before real crystallography happened. And the mathematicians took the lead in this regard because they liked the idea of having lattices, group theory, and that sort of thing. And these folks here a lot of their names are still well known, like Schoenflies. If you've studied group theory, you've probably studied the Schoenflies method, which isn't quite the same as the one crystallographers use, but it's very similar. It's actually a one-to-one correspondence. And then they developed the idea that there were 230 possible space groups, which is point group plus translation. And Schoenflies defined a crystal in a way that's more modern, a solid, homogeneous substance, which the properties are generally dependent on the direction and varying depending on such direction, following fixed laws of symmetry. So we're going to talk a lot about symmetry. It's awfully important. Okay. There was some disagreement among these mathematicians because in some of these groups, they had too many items in the group because they didn't understand how one particular setting was the same as another one. But I won't go into that. That's kind of an interesting story, but it would be kind of time-consuming. So here's a quote from Alice in Wonderland. "Thank you, sir, for your interesting story, but she could not help thinking there must be more to come, so she sat still and said nothing, like you." Okay, so really the modern ideas are only about 100 years old. Pretty amazing when you think about it. And there was no way to actually find out at the beginning that they were periodic. But it happened pretty rapidly at the beginning of the 20th century. First of all, we had Röntgen, who was a physicist and used cathode ray tubes. You've probably heard of him. So he's credited with discovering X-rays. So he had a cathode ray tube, and for some reason he covered it with heavy black paper. I'm not really sure why. And I don't know what the anode was in his cathode ray tube, but it would be some metal. Probably doesn't matter what metal. Anyway, he had a sample of barium platinum cyanide sitting across the room, and that's a luminescent material. And when he turned on his tube, he noticed that it was luminescing way across the room. And he was really surprised, as you can imagine, and he didn't know what was causing this. And he's the one who coined the term X-rays, X meaning we don't know what it is. But then he did a whole bunch more experiments, where he tried blocking it more, putting other things across the room. There's a very famous picture of his wife's hand in front of a photographic plate across the room, and a very nice image of her hand, and you can see her ring. I didn't bring that picture, but you can see it on the web. It's a very famous picture. And just probably within 10 or 20 years, people were using X-rays for therapy, looking at bones, broken bones, and that sort of thing. And when I was a child, they actually had an X-ray machine in every shoe store, and they looked at your feet with X-rays. Think about it. Probably not a good idea. They don't do that anymore. So anyway, he announced this discovery in about 1895, and in remarkably short time, really, people were starting to experiment with these X-rays. So Max von Laue in Munich, Germany, was given a lot of credit for the early understanding of X radiation. He knew that it was probably electromagnetic radiation of very high energy, which it is, higher energy than just visible light. And he understood that if there was a repetitive motif within the crystal, that there should be some kind of a interference effect, just like you get with slits, So you get destructive and constructive interference. But his initial experiments failed, and he didn't see anything. And then he kind of thought, so the story goes, that maybe whatever was in these crystals was moving too much, and that we were getting a lot of interference from the motion, the thermal motion. And that's why we didn't see any constructive interference. But I like this part of the story. He had a graduate student, Walter Friedrich, and as an assistant or postdoc, I'm not exactly sure what the proper title was, Paul Knipping, who wanted to try it again. And they tried every possible arrangement of putting the crystal near the tube that was producing the X radiation. And finally, and then they had a photographic plate. Finally, they got a diffraction pattern. And that was first published in June 1912. And it was only a couple of years later that scientists were going crazy playing around with this idea of diffraction. Interestingly, even though the graduate student and the postdoc got the experiment to work, Max von Laue was the one who got the Nobel Prize, of course. But he was a brilliant scientist as well. So here's a picture of von Laue. One of the first Nobel Prizes also. So this was the prize, confirmed that X-rays are a form of electromagnetic radiation and that crystalline materials consist of organized three-dimensional arrays of atoms, molecules, or ions. So he got it right. So what's so special about the X radiation, the wavelength or the energy of this radiation? I think of it in terms of wavelength, but of course you could call it kilovolts or whatever you want, kilo electron volts, etc. So the typical wavelengths that we use nowadays in the lab are based on molybdenum being the target anode material to produce the X radiation, or copper, although you can use many other metals. You could use silver, gold, whatever, get different wavelengths. But these are the most common ones, and there's reasons for using one over the other, which I'll go into later. But the crucial thing is that it's kind of the same order in angstroms of a bond. You know, we think of bonds as ranging like between about maybe 1.1 and 4 angstroms, something like that. So in order to get the interference effect, you need to have a wavelength that's of the same order. The thing is that you can't use just a microscope to see it. It's not visible light. It's too high of an energy. So then what? What do you do? Okay, so comes along to the Braggs. So William Henry Bragg was a professor, and his son was a new professor, William Lawrence Bragg. And Bragg, the son, is the one who developed Bragg's law, which is still used, still perfectly correct. I'll give you that on this next slide or two. But between 1912 and 1914, by using diffraction, he got these structures of the alkali metal halides and iron sulfide, diamond, and zinc sulfide. So this was all using photographic film, and we continued using photographic film until about 1950, before other kinds of detectors were invented. We were just talking about that. We both sort of got into it when those were still around, and I used film too when I started. So here are the Braggs, William Henry and William Lawrence. They also got a Nobel Prize in 1915, and I think that the son was the youngest to ever get a Nobel Prize, actually, and well-deserved, I think. He really was the one who described how you could get a structure from the diffraction of X-rays, and he didn't do it the way we do it now. He guessed pretty much at the structures by looking at the morphology of the crystals, seeing that, say, salt crystal was cubic, so maybe the atoms were arranged, like sodium chloride. He was right, so these were all simple structures that he did, of course. There have been some other father and son pairs who received Nobel Prizes. I don't know if you realized Arthur Kronberg, who got a Nobel Prize in crystallography, macromolecular crystallography, and Roger, the son, got the Nobel Prize in 2006. So there's a father-son case. And then Niels Bohr in 1922, and Aga Bohr, it got physics Nobel Prizes in 1975. Who? Corey, yeah. Mm-hmm. Yeah. Oh, and then there's mother-daughter too. Yeah, the Curies. It's not just father-son. Yeah. Mother-daughter too. Yeah. Amazing. Okay, so these are some pictures that I took a long time ago on photographic film. These are what we called axial photos. Did you get axial photos? So I saved these over the years because they were pretty nice ones. And what information you can get from these are unit cell dimensions, which I'll go into a little bit more later. Also by the symmetry of these. Each of these has mirror symmetry, if you consider the mirror to be in a horizontal line through the middle of the photograph. Can you see those? I don't know if it's real easy to see it, but that tells us that there's, yeah, it should be. There it is, yeah. So across here, there's a mirror. And so, let's get closer too. So okay, here's the mirror right here. So see those little two spots there, those two, they look about the same. Not only in position, but also in intensity. There's one, and there's one that match, there's one that match. So all three have similar mirror symmetry going across, which was a sign that it was what we call an orthorhombic crystal. So we got crystal system, we got unit cell dimensions, and all sorts of stuff. We had to do this before we even began the rest of the data collection. And this could easily take a week if you weren't very good at it. Okay, so things were harder in those days. But anyway, that was a nice. And next, I'm going to show you Bragg's law, which you probably learned in general chemistry, but they didn't tell you much more about it. They just sort of put it up there and say, so this is Bragg's law. Okay. Okay. So this is a simple view of Bragg's law. There's, you have to kind of change it a little bit when other things happen. But we think of each X-ray beam coming in sort of as a photon, sort of, hitting the crystal, which is sitting right here, and bouncing off without any loss in intensity. So this is a kind of scattering that physicists, would call something. But okay, so then here's another beam coming down and hitting another crystal. Okay, or you can think of this as an atom in the crystal, or whatever, but they're related to one another. The point is, the path length differs if you're this beam or if you're this beam. And you can calculate the difference in the path length by just using some geometry, right? It's just this distance here. If the path length is such that you get constructive buildup of these waves going this way, this way, this way, then you see a diffraction event. But if they're off that condition, then there's nothing there. So by doing the geometry, you come up with Bragg's law right here. So in lambda is the wavelength of the radiation, equals 2d. This is d, the distance between these planes, sine theta, and theta is this angle of diffraction here, which is equal to this distance here, or this angle here. Anyway, it's pretty amazing, I think, that he came up with that. So the reinforcement just happens millions of times during a data collection, but only in certain directions and at certain 2 theta values. And that's the process of data collection. So like...
Can that change with that also?
Yeah.
Right?
Yeah.
So that you don't have to come and...
Yeah, but I have my notes here. So I didn't have any notes on this one, just to show you a simple crystal structure of sodium chloride, which you've all probably seen before. There is a crystallographer who fell in love with crystallography on stamps, and I have a PowerPoint, but I probably won't have time to show it, of all kinds of stamps that have been made showing famous results from crystallography. It's really quite fun to look at. It's historical in itself. So this was one of the stamps that he had. Okay, so this is all a repetition, but I'm just showing you. Okay, you study matter in the solid state. Crystals form periodic arrays that diffract X-rays. The diffraction pattern is collected in 2 dimensions. Pretty much that's true. People who do neutron diffraction will use 3-dimensional data collections because the neutrons are very expensive. So they try to capture everything they possibly can. But for X-rays, we either use film, or we could even use a point detector and just capture one event at a time, or we can use modern day, like CMOS or CCD detectors, which are plates. So we're going actually back to the film picture because we're using a 2-dimensional detector nowadays. So once you have your crystal, you mount it on usually nowadays people use these very nice mounting pins and put it on the diffractometer. And on the next slide, there's a close-up of where you have your crystal. Usually it looks something like this. There's a cold stream that's coming down, hitting the crystal, which may or may not be at an angle, but anyway, a cold nitrogen stream to keep everything cold. Crystal sitting right there, you can't really see it. X-ray beams coming in here from the right. There's a collimator there to make it a certain size. And then this is the face of the 2-dimensional detector. Okay. So that's kind of the way it's all set up. And then there's another old picture here that shows a little bit more. So this is assuming that you had a tube. Nowadays, we don't always use tubes. We have other kinds of sources. But if you had a tube, this would be like a cathode ray tube. So there's a target metal here. Again, that would be considered the anode, and it could be copper, molybdenum, or silver, or something like that. And then it's bouncing off through a collimator down the line until it impinges on the X-ray, on the crystal. And then you get diffraction events coming off at all different angles from the crystal. And they end up as spots on the film. And then that's not the end of it, though, because there's more information to be gained. So what you need to do is change the angle of diffraction and rotate this crystal around in different directions. So a modern-day diffractometer usually has at least 3 different angles that are changing, so you get all these different orientations. Sometimes 4 different angles, 4 sets of angles, sometimes only 2. But you probably end up with many thousands of spots in a typical data collection. And it might look something like this here. Bunch of spots. But going back here, back to this one. Okay, I pretty much, I'm going to be going over this, so I'll skip that slide. This is what I was saying about, though, having a lot of different images that you need to then sort of stitch together to end up with a file, which we call the HKL file, and what that means will become clear, and ultimately get this crystal structure. And so this is actually an inverse process. A lot of people walk into the X-ray lab and they look at this picture and they say, oh, so that's my structure? But no, it's not your structure. You have to do a Fourier transform procedure to get to the real structure. So that's not the structure, but that's the information that you need to get the structure. Okay, am I going too fast? Questions, anybody? Yeah? Okay. So this is a nice example of what I was saying about the Fourier transform. So you can go either direction. For example, taking in this case a 2-dimensional array of the same pattern, which is what something crystal would look like in 3 dimensions. And then its Fourier transform just looks like a bunch of spots like that. So you have to do the math, go back and forth, go from the spots to what caused the spots, right? That's what we want to find out. Okay. So some of the cool things that I have done over the years, I just wanted to mention a few of them. This is, I think I said that I was very interested in Fullerenes. So in this case, you have a C60, which is a ball of 60 carbons. It's like a soccer ball. It's been derivatized with a phosphine. And the phosphine has some of these long arms coming off of it. And in the crystal structure, you have these incredibly intimate pi-pi interactions where the curved parts of these phenyl rings made up with the curved surface of the C60. And it was such a cool hacking pattern. I was so excited when I saw that. At the time, we weren't sure how it would end up. We couldn't know until we did the structure. It's pretty nice. And other people have seen this kind of thing. It's called phenyl chelation. Did you have a question? Okay. Yeah. And this was, I think this is the structure that I did with Christine Dunham at UC Santa Cruz. She was a graduate student with Glenn Milhauser. I believe this is my most cited crystal structure. And she made this crystal. So it was a copper complex of a chain of just 5 amino acids, a hydrate, and at the time it was implicated in mad cow disease, which was at the time there was a lot of fright about mad cow disease, though it never really happened that much in the US at least, a little bit in the UK. But this paper has just really been widely quoted because a lot of people were interested to see that maybe copper was involved in causing this, what do they call them, amyl proteins or something in the brain. So anyway, Christine's gone on to be a famous scientist in her own right. So that was fun to do with her. And then here is a natural product, believe it or not. So in the oil industry, you know, they get out all these different anes, right? Hexane, pentane, octane. Octane's the one that we want to use for gasoline, and so on. But methane they use for fuel too. Well, at the end of the barrel, there are solids, and the solids are these kinds of things. So they're also hydrocarbons. They only have carbon and hydrogen in them. But they tend to be solids, and so they don't actually get extracted along with all the other gasoline type of things. And I had a collaboration with some folks at Chevron Oil to discover what these were, and then they went on to try to find a use for them. Unfortunately, they never did. But again, you know, the structures are so cool. So this is kind of related to adamantane, but it's a bigger one. It's a bigger ane. It's a pentamantane. And there are many different isomers of this as well. And this is, ultimately, I can't remember how many structures I did, maybe 20 or 30 of these things. A book was written about them. They're called diamondoids. These are all carbon-carbon single bonds, but the lengths, and then there's hydrogens. The lengths of the bonds kind of depend on the position in the molecule, but the average distance between two carbons, with one of them having a hydrogen, is 1.546 angstroms, and that's pretty close to the distance in diamond itself. Maybe it is almost within the standard deviations, it's the same. So that's why they're called diamondoids. They make really beautiful crystals. So I just think I have one more to show you that. Okay, again, going back to Fullerenes. So here's C60, which is a ball shape. But you don't have to have just 60 carbons. You can have many more. You can have 90. You can have, there 96, 100. This is a fullerene that has stuff inside, 2 lanthanums. And this one has 2 samariums inside. It's 104 carbons. All of those balls are comprised of only hexagons and pentagons. In fact, always 12 pentagons, but different numbers of hexagons. So for people who love symmetry and geometry like I do, these are really fascinating molecules. And I've done, like I said, a lot of work with them. And we call these nanocapsular because they're sort of, these particular shapes are very elongated, so they're looking almost like a carbon nanotube, but a smaller version of a carbon nanotube. But that's another reason why they're interesting, because in a nanotube you kind of wonder, well, what's at the tip of a nanotube? You know, and we know now pretty well what the tips must look like. Oh, one more example. Okay. So this was pretty recent. This was just published in 2015. It was a collaboration with these folks here. I got the crystals from Alexei Popov, who is at Dresden University in Germany. I get crystals from all around the world, as some of you know. And this was a complete surprise, absolutely complete surprise. He knew that it eluted in a funny place in his HPLC, but no one expected it would be this. And it has a heptagon. You see this ring right here has 7 carbons in a ring. And so that's a violation of kind of the rule that fullerenes are always just pentagons and hexagons. And since then, we've discovered a couple other ones that have heptagons, and I think we'll still find more. We still have never seen like a 4-carbon ring, a square, in any of these, but that may come up too sometime. And this is also one that has stuff inside, so nitrogen, 2 scandium, lanthanum. Anyway, I'll talk about these in my seminar on Friday if you're more interested in hearing about fullerenes. Okay, so one more thing is that the year 2014 was declared the International Year of Crystallography because that was kind of 100 years since crystallography really took off. Morocco actually was the country that proposed it to the United Nations. The United Nations picked it up, and there were lots of celebrations and crystal growing contests and all kinds of neat things going on that year. If you're interested at all in that, there's this website that tells more about it. Okay, and then this is kind of the last one in this group. This is a movie of crystals growing. So how many of you have grown crystals? Yes? Oh, good. A lot of you. Good. Okay. So maybe we could share together, when I get to that, methods that you have for successfully growing crystals. A lot of people have called it an art, and it is in a way. Sometimes you get them in ways you never would have expected. But I have some favorite ways, and you may have too, so we'll talk about that. Now, let me see what time it is. It's 10 after 11. We got started kind of late. We could go on and start the next presentation for just maybe 10 minutes or something like that. Would that be enough for the morning? Okay, let's do that. So this concept of the lattice is really, really crucial to understanding crystals. So let's just do a little bit of this presentation. So again, we have this interference phenomenon. I keep mentioning that. What a lot of people don't realize is that the scattering is actually off the electrons. It's not off the nucleus. So the result that you get is a little bit distorted because it depends on the positions of the electrons. If you want to know the exact internuclear distance between atoms, there's a couple of different ways you can do it. One is to use neutron diffraction. So neutrons impact the neutrons and the scattering is off the neutrons. Or you can use ultra, ultra low temperature crystallography, like with a helium cryostat. So you're measuring everything at about, say, 10 K, something like that. And at that temperature, there's not much thermal motion, and so the electron cloud is a little bit tighter to the nucleus, and you get better internuclear distances. Okay, but in order for this to work, you have to have a regular repeat. So if your crystal is cracked, let's say, or it's just not really a very good crystal, your translational symmetry isn't very good, and your diffraction isn't going to look like a tiny little spot. It's going to look all smeared out. Okay? So crystallinity is really important for getting a crystal. And again, we will go into that a little more. And another thing I wanted to mention, though, is this idea of the lattice is not the same thing as the structure. And that's very confusing, and people misuse that all the time. They'll say, oh, the lattice contains blah, 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 but the lattice is actually a mathematical concept. It's an infinite repeating pattern. It's not the structure. So try to avoid saying the word lattice when you're talking about the structure, okay? And in the, if you have everything correctly done, the smallest repeating unit is called the unit cell, or in some cases the reduced unit cell. So let's just look at a 2D example. So I have a two-dimensional unit cell there, kind of shaded in, and a couple of objects in it. And the two directions are A and B. And there's an arbitrary choice of origin there, so I just put it in the lower left-hand corner. The angle between A and B is also always called delta. Okay. And so here you see 3 unit cells. It didn't really matter where I put the origin. I'm just showing that all you have to do is slide over by a translation of 1 unit, and you get to the next unit cell, and so on. And they all look exactly the same. So just imagine that in 3 dimensions, and you've got your crystal. In fact, it doesn't have to be this unit cell. All you have to have is a regular repeat. So, for example, I've taken the same thing and I've drawn in a different unit cell. See how here it was like that, and here I've put in some lines defining a different unit cell. The only difference is that the angle gamma is different, the lengths are different. Actually, though, you can show by geometry that the volume is the same, as it should be. It's just another choice of the unit cell. And the places where, say, there's an origin or the terminus of the A or the B vector doesn't have to hit anything. It can be in the middle of nowhere. It just has to be a regular repeat. Okay. They don't have to touch. So the conventions are, you all probably know this already, but in 3 dimensions, the unit cell has lengths A, B, C, and the angles between them are all like alpha is the angle between B and C, beta is the angle between A and C, gamma is the angle between A and B. And you should have a right-handed coordinate system. Now, the software that you use will do this for you. You don't really have to worry about it that much. It's going to find the acceptable unit cell. So for example, by acceptable, I mean, if you could have a very, very acute angle, it won't pick that one. It will pick a unit cell that has probably the closest angle to 90 degrees. It's easier to see, and that's what the International Union of Crystallography wants you to choose. And the software knows all that, and so it will choose the best one for you. Now, again, going to the next unit cell over is just translations. So we could call that a unit translation. So as you move across, say, the A-axis, you go to the next unit cell over, and you could say that the position P prime is just P plus 1, for example. Yeah, I've written it down below there. I guess I skipped a step here. I should have mentioned that X and Y are actually the coordinates of that point. And the coordinates that we use are fractional coordinates. So the lengths of X and Y are not necessarily the same because they depend on which A, B, or C vector you're using. So say if this is the origin, this would be 0, 0, and this would be 1, 0. Okay? And halfway in between would be a half, 0. So it's a fraction of that length. A third of the way down would be 0.333, 0. So if you add, if you look at, say, this position right here, what was xy becomes x plus 1 and y, going that way. If you go this way, then you're decreasing in this direction, right? So that would be at x minus 1, y minus 1. Let's see. Or y, did I do that right? No, it should be x plus 1, y minus 1. No. I think I'm looking at the wrong one. It's here. Okay. That should be x and y minus 1. You agree? Okay. So sometimes it's it's hard, but be sure that you are not doing 1 minus y. It's y minus 1. 1 minus y would be a different number, right? Mm-hmm. Okay, let's just do one more. So I should have put this slide first, perhaps. So crystallographic coordinates, also called fractional coordinates, some other names too, are what I just described. So it's a fraction of the amount that you go across from 0 to 1 in each direction. I guess you should just think of those A, B, and C as being unitary vectors, if you like. And so it's a vector quantity. And to get the distance between two atoms, you would just take the difference between the two vectors, right? So like A2 minus A1. If it's an orthonormal unit cell, it's really easy because you can just do it by Pythagorean. And it's very easy because all the angles are 90 degrees. And you don't even have to do it because all the software does it for you. But if the angles aren't all 90 degrees, you probably don't want to do it by hand. It's a complicated equation that I gave there. Cartesian coordinates are, you can take your unit cell and your structure, you can convert to Cartesian coordinates. However, you lose all symmetry information if you do that. But you imagine that you've put it into a cell that has lengths of 10, 10, 10 angstroms and 90, 90, 90 degrees. In some cases, it's useful to do the Cartesian coordinates. But again, you lose symmetry information, so you have to be careful with that. Okay, so I think we should just stop there, and next time we'll go talking about lattices, and yeah. I think, maybe this is just a review for you. Maybe it gets you thinking about it more, I hope so. But eventually we'll get down to the nitty-gritty of actually figuring out a structure, okay? So let's reconvene, I guess, at 3. Is that right, this afternoon? Is that right, Samkar?
Yeah.
3. Mm-hmm.
So 3 o'clock will be at here. Now, plus 3 to ask questions after every lecture.
Mm-hmm.
You can ask questions, you can interact. That is the beauty of this.
Oh, yeah, I should give you my email, too, if you want to email me. Okay. Because I don't have an office here. I'm over at the guest
No,
house.
but they can talk after the lecture.
Yeah, too.
Because
Do that.
if you start getting email, then
Oh,
you'll
I'll go crazy.
be crazy and it is not
Yeah. Okay.
thousands of emails that pick up. So one thing is that after every lecture, they have some questions. They can raise their hand
Mm-hmm.
and they can come or close to you, and they can also talk.
Right.
So whatever way you think.
Right.
So what I could see today is that he has given a brief overview, like starting from how it originates and then what it can do, solving structures and many aspects. Down the road and the next several days we will hear a lot of interesting aspects of crystallography. I should remind you, crystallography is not just solving a structure. Please understand, many of us are doing that. We get a structure, we are so happy. My students or even other students in the department also, they come to me, sir, I have a structure. But not many structure is in the publishable format. Because there are lots of problems. You publish today something, if it is wrong, after 2-3 years, you may have to withdraw the structure, withdraw the paper.
Yeah.
Telling you, remember, the Rangamanti came in paper.
Mm-hmm.
They claim something, and
They have to retract it
They
then.
have to retract.
Yeah. Yeah.
So don't think like that. Oh, I have a structure and I have to publish.
Yeah.
Because that is more dangerous than not publishing. Because you publish and after 2 years or 3 years you have to withdraw that paper. It is damaging not to you, for everybody.
Yeah.
For the institute, for the department, for your supervisor, for your own career, your
For the whole-
PhD can be withdrawn.
For the whole community. Yeah.
Whole community. And I know that some Chinese university was banned.
Oh,
But
yeah.
you cannot submit any paper from this institute.
Yeah. Yeah.
So crystallography is not just solving a structure, getting some information. It's not like this.
You have to learn to love it.
A lot of things and correctly.
Yeah.
That is more important. So more you know, more you will learn. Something, some people say that, sir, I have a structure, I know exactly. No, crystallography has lots of limitations. That's the reason why in a publication, in a good publication, like Jack's, Rangamanti, Nature, Science, you need to have supporting evidence like NMR, like mass.
Mm-hmm.
Because crystallography, she will be telling all these details, like similar electron density, they cannot distinguish.
Yeah.
Hydrogens cannot be precisely located.
No.
There you need to do neutron diffraction for that. Unfortunately, we don't have.
Well.
So please try to understand, and slowly she will be telling. Okay. And what are the things you need to look at? Not only just R parameter. Many students, what they do, they the solvents are there, they somehow put some atom oxygen, nitrogen and all this. They get R value, sir, हमारा R value बहुत कम है. It's not enough. People want to know what you have in the entire lattice.
Yeah.
Okay. So all these techniques you have to understand how to crystallize. Many students come, sir, somehow I am not getting crystal. So there are beautiful techniques available. Like one of the techniques is co-crystallization. So, they are successful in growing beautiful crystal of fullerene with some porphyrin.
Porphyrins, yeah.
Please understand that fullerene, if you grow the crystal, it will be highly crystalline. But that is probably cannot be, you cannot get more information because there can be several orientations of highly disordered.
Yeah, it's
So
a ball, it
gives
rotates.
nothing. It gives nothing.
Yeah.
So these are the techniques we will be teaching.
Yeah.
And I am sure that the lectures, whatever she will be giving, will be exciting for you. So my appeal to you all is that please come in time and attend all the lectures. Otherwise, it is just like I used to tell to my student when I teach the class, that it is just like a movie. Okay? It has a continuity, it is entire story. If you come one day and skip one day, come another day, looks like that you are watching some movie and after half an hour you are throwing out, you are asking to go out and come back again. So you will not enjoy.
Right.
Okay?
Right.
So please, she is a very renowned crystallographer, scientist, very nice and very approachable. And that's what I thought that probably she will be the best person to teach you and to publish or to put it in the right direction, because that is very important. Just having Excel structure is no meaning, it's of no use. Okay? Thank you so much.
Okay.
So 3 o'clock.